And hello, welcome everyone excuse me, to this video of convection heat transfer. Last time we were talking about let's see, oops, yeah, we were talking about this. We're talking about how to apply the Blasius solution to temperature profile using the Reynolds analogy in the special case that Prandtl number is 1. Okay, however, of course, we know that's not always the case, so we want to take a look at the cases where the Prandtl number is not 1. Then how do we solve such things? So I'll be referring to Adrian Bijan's convection heat transfer. Okay, you can look for it online, and I will be citing it as well. So first, I'll just demonstrate. Demonstrate to you how to get the bibliography stuff. So I search for convection heat transfer by Adrian Bijan in Google Scholar. So do go to Google Scholar, and under that you search and you cite BibTeX. Okay, copy this, and this is the manual way of doing it. I do cover if you want to use Mendeley, but this is the manual way. So let's open up bibliography.bib, and then we'll have this 2013 convection, and the other one will be fundamentals of momentum, heat and mass transfer. Okay, under these two double apostrophes is the citation thing. You just copy and paste this text into your BibTeX. Okay, so if nothing goes wrong, all of this should work. Okay, I'll be closing this. I don't need that anymore. Okay, then I will be citing. So to cite, let's just do cite. Okay, and I'll probably have to close and open again. That's the weird thing with LaTeX. Okay, cite. Yeah, let's see whether it turns out. Yes, you'll have, once you close and open, you will be able to see this auto-filling thing here. So you'll be cite Bijan 2013 AA convection. And how will that name come about? It is the name that you put over here. So I just copy and pasted that from Google Scholar. Then I'll cite the other one as well. Cite okay, a Welty 2014 fundamental. So that's how you cite it in text. Use the backward slash and cite button. If you want to do LaTeX, then you have this kind of thing, but there's no bibliography yet. So I made a part for bibliography, and then you need to just put backspace print bibliography. Alright, and that's how you do it. Okay, enough of bibliography stuff. So how are we going to start? Okay, so now the references are out. Very good. How are we going to start how are we going to start getting some similarity solution for the temperature profile? Okay, so again, we will use what we have done before as a backbone. Okay, we will use what we have done before as a backbone based on the Blasius solution. So this is the Blasius solution. If okay, from Blasius solution. Alright, so we have the Blasius solution, and of course the relevant boundary conditions. So let's see, non-dimensionalizing will be here. Alright, so this is all our Blasius solution, copy and paste, or rather the Blasius set of differential equations that we copy and paste. And some useful derivatives previously derived are as follows: the del eta del x star, del eta del y star. Okay, however, the del eta del y star will be slightly different because we are using thermal boundary layer, I think, to to actually do something about it. Okay. So from hydrodynamic BL, hydrodynamic boundary layer, this is where we start. And of course, the last but not least, we need to have our temperature equation or energy equation, which deals with the temperature. So let's go with the energy equation. Okay. So this is our energy equation right here. Okay. Right. And I'll just put this on top, just in case you want to know where some of where I refer. Okay. So this stuff is the energy equation, and one I want to use is the energy equation where I already half non-dimensionalize it. Okay, so this is like, we non-dimensionalize halfway. Okay, so we non-dimensionalize halfway already. So you just take this, since half the work is done, we can fully non-dimensionalize it to get our equation. Okay, we half non-dimensionalized the energy equation during scaling analysis. Okay, so we will need to have some non-dimensional numbers or something like that. Okay, and then we will be able to see some order of magnitude analysis as well. So that's very good. Okay, so I think most of it has been non-dimensionalized already. You just have to collect the terms together, and of course not just non-dimensionalize it, we need to maybe I'll say we non-dimensionalized it. We just need to convert it to some similarity to include similarity variables. Alright, so that's the whole idea here, that we want to use the same similarity variables we did before. Okay, now we'll want to use the same similarity variables we did before. Okay, so eta will be the similarity variable of choice. Of course, the derivative of eta is going to be slightly different now, because our how do you say, the way we define eta and everything is going to be slightly different. Okay, so yes, without further ado, let's just begin. Okay, so believe it or not, we may not be able to use some of these derivatives later. Well, we'll need to come out with some fresh derivatives, because the way we non-dimensionalize eta and everything is a bit different. I mean, we non-dimensionalize this temperature equation is going to be very different from what we did before. Okay, so what's good? We already have theta over here. We have theta over here. We just need to get rid of the x and y's. Okay, so the whole idea now is we convert x and y's to include our similarity variables. And of course, u star must be u star and v star should be turned into some form of f, where f is this string function right here. So we'll probably need to refer to what we did before. Okay, so let's get rid of the u stars first. Okay, so we make substitutions by making substitutions to get rid of the u. So u star equals to fraction f prime over 2. So let's start with that. Okay, again, if your differential equation is slightly different, don't worry. Some textbooks do like to use different forms. I will just use this form. the idea is again more or less the same. Okay, next I want to search for V star. Okay, do I have a expression for V? Oh no, I do not have it here. Let's see whether I have it in. Okay, let me find it first. Alright, so anyway, based on the LaTeX files I was doing, okay, V will look like this. Okay, V will look like this. Okay, of course, if you want to include V star in there, you can, but yeah. So we'll try to use this form of V, and then we'll just convert it to V star. So V equals to minus half. Okay, let me look for some steps later. ... Yeah, so V equals to, yeah, let me copy and paste this over, and we'll have to non-dimensionalize it. Alright, let me cancel this. Yeah, and compile. Okay, so one good thing about this is most likely your f prime should disappear, if I'm not wrong. Yes, your f prime should disappear. Yeah, your f prime should disappear, and basically we should get everything condensed to a stream function. So how did we non-dimensionalize V? Okay, so we non-dimensionalize V. If I can remember, I'll just have to go back and refer. All the notes are there. How do we non-dimensionalize V? With some characteristic V velocity. Vc equals to fraction U infinity delta P, those are momentum boundary layer, over L. So we can use that as a way to help us non-dimensionalize. So V equals to V star into Vc, which is all of this here. Okay. So okay, so now we'll just shift some of these variables over. So for example, delta P over L, I will shift it over, so it will become L over delta P. Okay, next thing to shift over is U infinity. So this one will come to the bottom, and then we'll just divide throughout. We should be able to get some sort of Reynolds numbers there. So we divide throughout by U infinity, we will be getting U infinity in the denominator this time. Right? Because when you bring the U infinity into the square root, it becomes a square kind of a thing, and then the whole left hand side should be non-dimensionalized. Okay, so I will just do it in this form. Yeah, Re x to the power of minus fraction of half. Alright, so that's how we get our V star. And that's part 1. Oh wow, that's so ugly. Okay, I should use curly brackets this time. Alright, so that's one. And we'll substitute back in, and we'll probably get a little bit of a mess. But the hope is that some of this mess will start cancelling out. Okay, some of this mess will start cancelling out. Okay, that's the hope anyway. So let's just do it. Alright, yeah, so we substitute this back into our energy equation. And what do we get? Okay, what do we get? Alright, so let's substitute U star in there. Then we'll get a form of F prime. So we have a F prime over 2 for U star. And V star will be all of this bunched together. So I'll put left and right brackets here. It's going to be very long. Okay, so now this part looks a little bit ugly. Well, let's begin by cancelling out the delta p's and bringing the L out. So let's bring the L out and we cancel out the delta p's. Alright, that's one. Okay, so this is the first part we substitute. The next part is that we need to substitute out this y star and x star. Now we need to substitute out y star and x star, y star and x star. Okay, for eta. Okay. Now, a little bit of a problem here, we cannot use what we were doing before exactly the same way, because these are actually based on different length scales altogether. So we might have to start like from scratch. Okay, so let's start by defining y and y star. Y star equals to fraction y over delta t, right? Okay, because delta t is the thermal boundary layer. It's our what do you call that? It's our length of interest. X star equals to fraction, okay, fraction x over L. I'll close it up, where L is the length up to which we are interested. Okay, so maybe we can use the x derivatives there. Okay, let me do a double dollar sign so that it will become yeah. Let's see how much time. Yeah, I'll do a little bit more. Okay, so looks like for y y star we will need to like treat it with a little bit more care as compared to x star. Okay, so yeah, we'll need to deal with that. But let's see the x star. X star is more or less the same. Okay, we note the x star is the same definition as the non-dimensionalized. Okay, so if you're not sure why I can reuse some of this, please go and check out my Blazier's boundary layer in hydrodynamics or fluid mechanics. So that's where I get all these from. So this is like a continuation of that previously. So we know x star is the same definition as the non-dimensionalized x star used in deriving hydrodynamic boundary layer. So we use it again. Okay, we use it again. Okay, well, y star is a little bit different. Okay, y star is a little bit different. So we have this thermal boundary layer here. We'll need to deal with it. So let's copy and paste what we can use. So what we can use is let's see, where's the correlation? Where's the correlation? Yeah, this one. Del eta del x star. Or del x star del eta. So we can use this thing to perform our chain rule. Okay, so we see this del by del x star, and we can just start replacing it out. Replace leftmost term So where's the leftmost term? I'm talking about this del by del x star derivative. So we can just put this chain rule like so. Fraction partial by partial x star equals to fraction partial by partial of eta, and then you do a fraction partial eta partial x star. Okay, no problem now. So at least the leftmost term is now being replaced, and then we can just wholesale copy and paste it down. Of course, we need to know what this RE delta is. After that, I will replace, and then I'll make the terms clear. But first, yeah, let's do that. Oh shucks, I did not even copy it properly. Okay, I need to copy it back. Okay. So this is the fluid mechanics one. Okay, this is fluid mechanics part. We're dropping terms, simplifying. Where is it? Okay, let me find it first. Okay, here we are. Okay, I forgot. I need to copy and paste everything here. Okay, so here it is. This is the line I wanted, so that it can make life a little bit easier. So it's eta over 2 minus 2x star. Now, okay. Okay, now we are in business. Okay, so I think I can just delete the first one. It's kind of redundant. Alright, you see this? Yeah, I'm going to delete this one because it's like redundant. So basically what I proved is that del by del eta del x star is equal to eta over minus 2x star. So we'll just use that term to replace. Okay. Of course, we can bring out this del by del eta del x star. I mean, that's not a we are not differentiating that. We are actually just multiplying these two together, so to speak. So minus. Okay, we'll bring the minus sign out. Minus 1 over 2x star eta. Okay, so we can change the leftmost term here to include our similarity variable. Okay, and let me put the fraction properly. And we're almost done for this video. Yeah. Then I'll stop, take a break, and then we'll come and finish up the rest of it. So this part has to be substituted here. So this part has to be substituted here. No problem. So we have minus eta over 2x star. Yes, I think del by del eta is missing. So replace leftmost term, partial by partial eta is over here, which should be pasted here. And wow, what did I just do? Okay, let me try again. This one goes here. This one gets deleted, and this goes here. There we go. So we have a partial by partial eta of theta. So this is wrong. You got to just take a look Yes, now you got it. Okay, so I'll just remove the brackets for clarity, and then we're done with this one. Okay, so this term here is replaced by this. We'll just simplify this to theta prime. Okay, because that's what it is, theta prime. Just to like save some space, and just make things a bit neater. All right. So we have eta over minus 2x star here. Okay, so next video we'll need to start dealing with this del by del y terms. Okay, so we'll come back to that, and thanks for watching. I'll see you again. Hopefully haven't committed any careless mistakes, but in case you found some, just leave it in the comment section. I know I'm prone. Okay, it's just the truth. Okay, so thanks for watching. See you guys again. Bye bye.